All right.
Sure.
So welcome to the second day of VMCAI'. It's my great pleasure to introduce our invited speaker today. That's Javier Esparza. Javier holds the chair for the Foundations of Software Reliability and Theoretical Computer Science at the Technical University in Munich. And as you all know, he works in automatic program verification, program analysis, concurrency theory, and automata theory. He's probably most well known for his contributions to PetriNet theory, especially the unfolding approach, and of course his books on PetriNets with Jörg Diesel and Keiko Haljanko. But his talk today is about an exciting research program about a new normalization algorithm for LTL, which has led to smaller automata for LTL and has, of course, impact in many areas that are important to VMCAI', such as probabilistic verification and also automatic program synthesis. So Javier, welcome. We're very much looking forward to your talk, and the stage is yours.
Yeah, thank you very much. So thank you very much for the invitation, and thank you very much for the introduction. So as you can see, this is a joint work with Jan Kretinsky and Salomon Sickert, with whom I have worked on the general topic of translations of temporal logic to automata for a number of years. And very recently, Ruben Rubio joined the team. And Jan Kretinsky and Salomon Sickert, well, Jan is at TUM. Salomon Sickert is now at the Hebrew University of Jerusalem in the group of Orna Kupferman, and Ruben Rubio is in Madrid at Universidad Complutense de Madrid. Okay, so I think I don't have to introduce temporal logic to this audience, but as you all know, logics formalize fragments of natural language. And for example, propositional logic is the logic that formalizes the meaning of words like and, or, not, or if, then. And then temporal logic extends propositional logic so that it formalizes also the meaning of some temporal words like today, tomorrow, eventually, never, until, and a few others. It has been studied within mathematical logic for over 100 years. And for example, Lewis and Pryor are two important figures in this area. But I think it's fair to say that temporal logic remain exquisite, rare to exquisite flower in the corner of the garden until the 70s, when in 1977, Amir Pnueli proposed to introduce it as a specification language to reason about computer programs, and in particular about reactive programs in this very famous Fox paper. And, you know, and his observation was that when you look at temporal specification, program specifications in English, written in English, then you observe that actually they have this form. They are kind of sentences talking about jargon, but connected by means of connectors, which are on top of the usual Boolean connectors and, or, and so on, temporal connectors, words like eventually, always, before, once, and so on. So, and as these examples are taken from this very nice collection with about maybe 1,000 or so such specifications that Matthew Dwyer compiled. So I'm going to talk about linear temporal logic today. And then I am pretty sure that you all know its syntax, but it is going to be actually rather important to use a particular syntax, and that's why I'm going to spend a little bit of time introducing it. So first, look at this. You have here propositional logic, right? But in what is called negation normal form. So that means negations are only before atomic propositions. They are only found before atomic propositions. Good. Okay, so now then we are going to extend this with temporal operators. And the three temporal operators that we are going to use are the next operator. So tomorrow phi1 will hold. The until operator, phi1 will hold until phi2 holds, and phi2 is guaranteed to hold at some point in the future. And the weak until operator, which maybe is not so familiar to all of you. So the weak until operator is very similar to the until operator. It also states that phi1 is going to hold until phi2 hold, but now phi2 is not necessarily required to hold at any time. So it could be the case if phi1 holds forever, continues holding forever, then phi1 weak until phi2 is also satisfied. Okay, good. This syntax is already expressively complete in the sense that it is going to be it's going to be able to express all the properties that you can express in any of the syntaxes that you usually see in books or in papers. Now, some of you, maybe the ones who are more acquainted with temporal logic, may be asking, oh, but shouldn't you also include, since you are insisting on having only negations only before atomic propositions, shouldn't you include these two operators, the release operator and the operator called M, the duals of the until and the weak until operator? And the answer is, you can imagine that they are there. Okay, it's just that for expository purposes, I am not going to use them. But everything I am going to say holds if you include these two operators. And finally, in this talk, I am going also to speak a little bit about the history of LTL. And for that reason, I will sometimes refer to past LTL. And this is the extension of LTL with past operators. So for example, we have an operator for next, which means essentially tomorrow phi1 will hold. We can also have then a corresponding past operator, meaning yesterday. Yesterday, phi1 held, was true. Okay, so this is the syntax we are going to use. And then there are two abbreviations that I am sure you all know, F and G. F phi means eventually phi will hold. At some point in the future, phi will hold. And G means always, phi will always hold in the future. And they are abbreviations in the sense that true can be expressed, F phi can be expressed as this formula, and G phi can be expressed as this formula. And the thing that you should keep in mind for the rest of the talk is only that F is abbreviation, or is an abbreviation of an until formula, and G is an abbreviation of a weak until formula. Good. Okay, so we are set. And now, what happened after Amir Pnueli introduced temporal logic into computer science in the late 70s? So he embarked in a research program, which took him about 15 years, and in which he was joined, not from the beginning, but the later point, by Zohar Manna. And this research program culminated in two books, very famous books, published in 92 and 95. There was going to be a third book, which wasn't published in the end, but parts of it can be found in the webpage of the late Zohar Manna. And which was and when you look at the story, at the narrative of these books, which is the spine of this work. And the spine is a classification of the properties that can be expressed in LTL, in linear temporal logic, which is called the safety progress hierarchy. Okay, it is a hierarchy with 6 classes, and the expressive power goes in this direction. Okay, so the two more restrictive classes are the class of warranty properties and safety properties, then come the class of obligation properties, and so on, and you can move up. And these classes, they were, Manna and Pnueli gave them a semantic characterization and also a syntactic characterization in terms of past LTL, linear temporal logic with past operators. So for example, the warranty properties are the properties of the form F, eventually phi, where phi is a past formula. Okay, and if you move up, then you can reach the reactivity property and the reactivity class, and reactivity properties are conjunctions of formulas of the form Fg, so eventually always phi I holds, and GF, which infinitely infinitely often psi 1 will hold. Okay, and again, phi I and psi I, they are past formulas. Good, and the idea of this classification was that for each class, Manna and Pnueli provided proof rules. So their goal was actually to prove reactive programs correct with respect to specifications written in linear temporal logic. And for that, they were thinking their approach was logically oriented. So the approach was to give proof rules which allow to break down the proof of a program into smaller proofs until you reach proofs that you can conduct directly. And we are not going to get into those proof rules at all, but here are examples of the kind of proof rules that you can find in the books by Manna and Pnueli with a little bit different notation. So for example, this square is a notation for G, and this is a notation for F. But as I said, this doesn't really matter. The only important thing is that their approach was proof-oriented. It was oriented not towards finding bugs, for example, but towards proving programs correct. And, you know, all this program hinges on a fundamental theorem. Because as you can see here, this is not the most general kind of temporal properties. So it hinges on a normal form theorem, telling you that every formula is equivalent to a reactivity formula. So without this theorem, the whole building, in a sense, breaks down. So now, when you look at where can you find the proof of this normal form theorem? Well, actually, you don't find it in the books. You don't find it in the books because it is, as it is said, this is too complicated. It is out of the scope for these books. And in fact, you find it stated, the statement of the theorem, you find it for the first time in a paper published in 1985 by Lichtenstein, Pnueli, and Zek, okay, called The Glory of the Past. And you don't find the proof there either. And the only thing that you find there in that paper is this, that the proof is based on many previous results, including results by Bushi, by McNaughton, and by many others, which when combined yield the theorems almost immediately. Well, actually, if you try really to find the proof, then the only place where you are going to find it in the web, as far as I know, is the thesis of Lenore-Zak, okay, which was published 1 year later in '86. And now you can decide whether you think that the theorem is going to follow immediately or not, because when you look into the thesis, you see that starting from a past LTL formula, the first thing that Lenore does in chapter 4 is to translate the formula into something called a counter-free semi-automaton, then invoke the Krohn-Rhodes decomposition theorem to translate the counter-free semi-automaton into a star-free regular expression, and then apply a specific transformation due to Lenore herself in order to translate the star-free regular expression into a past LTL formula in the normal form, in reactivity form. And in fact, when you look at this last step, you see that it has a non-elementary blow-up. So actually, the past LTL formula can be not only exponentially or double exponentially or triple exponentially. It is a tower of exponentials. The blow-up is given by a tower of exponentials. Okay, and you can think, okay, well, probably somebody has improved on this. Well, actually, remember, this is 1986. And if you move 25 years forward, then you are going to find a paper by the late Oded Mala in this book, in memory of Amir Pnueli, where he presents a construction and says that, well, maybe it would be possible to extract from this and only a construction which is has only a triple exponential blow-up. Which again, it's, you know, it's still not so conclusive. So you would have expected that somebody else addresses this problem, but no, you know, the rest is silenced. As far as I can tell, nobody has addressed this problem after that, after Oded. And even though there is no lower bound. So this is a pretty amazing thing. You know, Amir Pnueli got the Turing Award for his work on temporal logic. Manna and Pnueli were two of the most important researchers of their time. Their book is the culmination of their work. This is the fundamental theorem in their book. How can it be that this question has been left open? How come? Well, if you want my, I don't know, and I think it's a bit of a mystery, but if you want my personal interpretation or my personal opinion of why this is so, I think that the reason is that in '86, So actually, you see this more or less the same time when Pnueli and Lichtenstein and Lenore-Zak proved the normalization theorem. At this, in this year, in LIX 86, Moshe Vardi and Pierre Wolper introduced the automata-theoretic approach to model checking, and in particular, the automata-theoretic approach to proving specifications in linear temporal logic, work that gave them the Gödel Prize, some years later. And I'm sure that you are all aware of this work, but in a nutshell, what it does is, or the idea is to translate the formula, the LTL formula, into an omega automaton, and then, and this is the key point, then essentially throw the formula away. Because from that moment on, in order to check that the finite state program satisfies the specification, you can just resort to automata-theoretic operations. So you don't need any other concept from logic in principle. Okay, and also what you are doing is replacing proofs by computation. You don't have to now construct any manual or computer-supported proof. You can just rely on automatic techniques. So this is, of course, a great improvement. Also because, you know, this algorithm, the algorithm they gave for translating the formula into an omega automaton, works for arbitrary formulas. So then you could say, okay, so then actually there is no longer a need for hierarchies, for proof rules, or action systems, or any of that logical stuff. All that is replaced by automata-theoretic algorithms. And so maybe you are all, maybe you are familiar, and if not, I very much recommend that you have a look at the Spot online translator that you can find in the web, where you can find also an online demo, which actually now visually can show you how this algorithm works, right? So here you have a particular LTL formula, and here is the Bish automaton that you are going to derive from it just with a one click in almost no time. So this looks like a very convincing reason maybe not to continue with the Manna-Pnueli program and try to find the blow up, the exact blow up necessary to normalize formulas. Still strange, right? I think it is still pretty strange. And we are going to come to this point, of course, a bit later. So in this, the idea is that the automata-theoretic approach, if you need a slogan, then what it does is to demote LTL to just syntax for automata. So you just have a new syntax for specifications, but you throw away everything else which you expect when you have a logic, like proof rules, axioms, and so on. Okay, and the automata-theoretic approach, in fact, was very successful from the very beginning and has continued its success for decades. In fact, so by 2004, it had been implemented in very sophisticated and very successful verification tools like the spin model checker, which probably you have all heard about. Then it was extended in the course of the 90s and the 00s to verification of probabilistic systems. And there are also very successful tools in the area like Prism, and this continues also its ongoing research. And it has also found, the automata-theoretic approach has also found a very important new application, which is reactive synthesis, the automatic synthesis of reactive systems from LTL specifications. It's a kind of a dream of computer science where you just give the specification of a program, of a reactive program, and then at the click of a button, you get an implementation. And since for the last 7-8 years, there has been a synthesis competition going on connected to the CAF conference. Good. So there is, however, these new developments in the automata-theoretic approach bring a very important challenge with them. And a very important technical challenge, which is reactive systems requires to translate LTL into deterministic omega automata. This is not the case for verification. For verification, it's okay, it suffices to translate them into non-deterministic automata, and that's what actually Vardi and Wolper did. If you want, if you are not interested in synthesis, you are happy with probabilistic verification, then you can relax this requirement a little bit. You may also translate into deterministic automata, that's already enough, but you can relax it a little bit by translating into something called limit deterministic automata. If you don't know what limit deterministic automata are, don't worry, I will tell you in a few minutes. So, and this challenge, you know, can be split into two parts. One is the theoretical challenge, which says, well, is this at all possible? It could be the case that there are no deterministic automata for some specifications. Maybe there are only non-deterministic automata, or there are no limit deterministic automata even. So the first part is the theoretical challenge. Can we always find such automata? And then the other part, this is the part, well, let me before moving to the next slide, maybe. And then the other part is the algorithmic challenge. How do you do that efficiently in case it is at all possible? Well, that it is at all possible was proved very relatively quickly. So remember that we are in the mid-80s, and by 88, okay, Safra has already shown that you can determinize omega automata. Okay, and actually, depending on, I mean, everybody will agree that the problem about limit determinization, whether for every specification you have a limit deterministic automaton, that problem was solved by the mid-90s by Kurkubetis and Giannakakis, and maybe even a bit earlier, depending on what you call a solution. Okay, so the theoretical challenge was solved relatively quickly, but what about the algorithmic challenge? Well, first, the algorithmic challenge is by no means trivial. So because the translations from temporal logic to deterministic omega automata, they have a double exponential blow-up, contrary to a single exponential for translations into non-deterministic automata. And not only that, because, you know, that's, of course, a serious problem, but there is an even more serious problem, which is that the translations as originally formulated by Safra and by Kurkubetis and Giannakakis, they are quite monolithic and very combinatorial. What do I mean by monolithic? When you look at the papers, what they tell you is, okay, given this formula, here is the equivalent automaton, the set of states is this, the set of transitions is this, and so on. The formula is written out of smaller formulas, but the algorithm, the translation is not following, is not respecting or profiting from that. It is just telling you in one go which is the final automaton. And what do I mean by very combinatorial? By very combinatorial, I mean that the states of the automata, they have a very combinatorial shape. For example, in the case of Safra's translation, the state of the Safra automaton, a state of the deterministic automaton, is going to be a tree of sets of states of the non-deterministic automaton. So you first translate the formula into a non-deterministic one, and then you determinize the automaton. And then this means that these constructions explode in your face, because when you start to construct the set of all trees of sets of states, for example, of depth 1, 2, 3, immediately you are going to go into very high numbers. Okay, and implementations struggle up to this day to control this combinatorial explosion. So even though the theoretical solution was there already in the late 80s, 40 years later, we are still struggling with this. So just to give you a quick impression of how how bad these problems are. So look at these are some numbers taken from a paper which was published 5-6 years ago at CAF. Okay, and where you can see the size of the automaton of the construction by Safra, of the automaton constructed using Safra's algorithm, using the state-of-the-art tools at the time. So we are about 5 years ago, right? And this on some selected formulas. So these are parametric sets of formulas. It doesn't matter what they really are, but notice that we can get larger and larger formulas by increasing the values of some parameter, for example, here j or here k or so on. Okay, and the size increases linearly with the parameter. And then here we can see how the size of the automaton increases when we increase the parameter. And then you can immediately see, for example, here that for these formulas, the ones here, the situation is really pretty bad. So even for a very small formula like F12, we are going to have already automata with about 100,000 states. And this is going to actually, since then you have to take the product of this automaton with another automaton extracted from the system, which can be very large. This is going to kill you almost immediately. So imagine, so I hope that you have all watched the movie Back to the Future, which was the title, the initial part of the title of this talk, right? And you remember that the protagonist is McFly. And imagine that McFly, after all his troubles in the Back to the Future movie, then he got into computer science and he got into verification, and he is now an IT expert in translations of LTL to automata, and he's has to fight all the time with this explosion problem, state explosion problem in the number of states of the automata. And he's just thinking, okay, so how can I do better in the future? And this is 2021 now, and how can I do better in the future? And then Doc shows up and tells him, you know, actually what you have to do is do better in the past. What we have to do now is go back to the 80s and attack once again the problem that Manna and Pnueli left open of which is the blow up in the normalization of LTL formulas. And of course, McFly says, but why? What does the one have to do with the other? You know, this is old stuff. I mean, who cares about that? And Doc tells him, okay, well, no, I don't have to explain you. I don't have time to explain you. We have just to go back to the 80s and do that. So then they both get into the DeLorean, right? And they travel back in time to the 80s. And we are back to the safety progress hierarchy. And we have back to the problem that while every formula is equivalent to a reactivity formula, there is a non-elementary blow-up involved, which prevents us from using this for anything. So now, in order to attack this problem again, McFly and Doc think about the alternation hierarchy, which is something that Manna and Pnueli already knew, right? This is still stuff that goes back to the 80s. And what is this? This is a hierarchy which looks like the process hierarchy when you display it on a slide, right? And but it is defined in a different way. So it is defined, you know, we are using a syntax in LTL where we only have until and weak until operators. And therefore, we can syntactically define some classes. For example, the class sigma 1 of formulas which only contain until, but no weak until operators. Or the class delta 1, where we only have, oh, sorry, this should be pi 1. There is a typo here. Pi 1. The class with only weak until operators. And then the class delta 1, which is the class of formulas which are Boolean combinations of sigma 1 and pi 1. And then we can move higher up in the hierarchy by considering classes with only, or with at most, I should say, at most one alternation between U and W. And it can be the case that U is the outermost operator and then weak until is the innermost operator. So you go from until to weak until when you go down the syntax tree of the formula, right? Then we call this class sigma 2, and here you have an example of a formula in sigma 2. We have the corresponding class pi 2, where the alternation is from weak until to a strong until, right? And then we have delta 2, Boolean combinations of pi2 and sigma2, and then we could define sigma3, pi3, and so on. But of course, what you are expecting, and indeed that's the case, is that these two hierarchies coincide. And as I said, this is something that Manna and Pnueli already knew. In fact, there is this paper in VMCAI'22 by Cheng, Manna, and Pnueli, which proves this equivalence. But unfortunately, this result does not help at all in order with the blow-up. So notice, by the way, that while this is a hierarchy where the formulas may contain past operators, that's no longer the case here. In this new hierarchy, the formulas only contain future operators. So this is the LTL that we all know, right? And therefore, this is already very important because it's telling us that for every formula with past operators, we can find another formula without past operators, right? And not only that, but of a very restricted shape. But unfortunately, it doesn't help at all with the blow-up, because actually Manna and Pnueli and Cheng, they were relying on the previous result, on the translations in this part of the diagram, right, in order to prove their new result. So the translations would still remain non-elementary. Okay, so, but at least we can now reformulate the normal form theorem and rewrite it, express it now as every formula is equivalent to a delta 2 formula. That's what the new normalization theorem says, still with a non-elementary blow-up. Okay, so now McFly and Doc start looking at this, and they come up with a new normalization procedure. They show that this terribly complicated proof where you go, to this counter-free automata, to these star-free omega regular expressions, all that is not going to be necessary. And how? What do they do? What is the first thing they do? They look at what you can call atemporal temporal formulas. And what is a atemporal formula? So it's a formula that if it holds at a moment in time, then it holds at every moment in time. And vice versa. If it holds, well, of course, if it holds at every moment in time, it is also going to hold at any particular time, right? So you may think that these are very strange, but no, actually very common formulas out of this are atemporal. For example, infinitely often A. If I tell you that today it is the case that infinitely often in the future A is going to hold, then this is also true in 10 days. And this is also true, it was also true 1 year ago, that infinitely often in the future A is going to hold. Okay, so somehow these formulas, even though they are temporal logic formulas, they have this eternal, they are godlike in the sense that they are outside time in this specific sense, right? And the key idea, the key new idea, is to treat actually these particular atemporal formulas, GF and FG, or these particular temporal operators, GF and FG, as first-class citizens. Okay, so we are going to consider now the syntax where we have the next operator until and weak until, and then we are going to have both GF and FG as new temporal operators. You should not look at them now as a combination of smaller operators. Look at this as a name for infinitely often and for always, from some point, always in the future. Okay, and then it is very easy, just by looking at the shape of the delta 2 class, it is very easy to rephrase the normal form theorem as in this way, to say that every formula is equivalent to a formula satisfying, and here come 4 conditions that together are equivalent to being in this class. And therefore, you can substitute the one by the other, right? And those conditions are just purely syntactic, telling you that when you look at the syntax tree of the formula, you will see no U under a W, and you will not see a GF or an FG under any other, essentially any other operator. that you will not see a weak until under a GF, and that dually you will not see a U under an FG. And now what you can then try to do is find, so imagine that you have a formula and you find a U under a W. Okay, so then can you try to find a rule, a temporal logic rule, which allows you to kind of remove this until, right? Or to solve this problem, replacing the formula with the until below the W by something where this particular problem, this particular until under a W is no longer there. And then you can try to do the same with all four. And it turns out that this works. It took us a couple of years of work, right? But it works. And it leads to what I jokingly, right, don't take this very seriously, like to call the Maxwell equations of LTL. This is just a set of 6 equations that give you a rewrite system which allows you to normalize any temporal logic, any formula of LTL into a formula of delta 2. And I would like to comment a little bit on about two of these. So just to show you what they mean, what that means. So what this expression means is we have a formula such that at the top of the syntax tree we have a W, and then on the left we have a formula which contains a subformula which is an until subformula. So these brackets are telling you that this beta u gamma is a subformula of alpha. Okay. And then the rule is telling you, so here you see, of course, that you have this until below this W, and then we are going to solve this problem, and we can do that by writing the formula, by replacing this formula by the equivalent formula on the right. And the meaning of this, for example, is, when you compare this with that, the meaning is, okay, replace the until by a W. Go to that until subformula and replace the until by a W. And when you go to this means go to alpha and then go to this particular subformula, beta until gamma, and replace it by false. Okay? So then, as you can see, we get a larger formula here on the right. But now this is a formula where this until is no longer here. And therefore, we have solved the problem. Notice also that, for example, here we have until. So there also we don't have any alternation and until below a W anymore. Okay. This, for example, is a law telling you that formalizing this idea that GF something is an atemporal formula, because what this is telling you is that whenever you have a subformula in a larger formula of the form GF beta, you can somehow move the GF beta up. Okay, so that it is a subformula means that you expect it to hold from some point onwards, but now you can move it up to the top, okay, here, reflecting this idea that GF is an atemporal formula. So as you can see, then you can bring them up, all GF subformulas, in this form, because now you replace here the GF beta by true and by false. Okay. So why do I call them the Maxwell equations? Well, first, remember, this is a joke, but there is a little bit of truth in it, in the sense that, well, of course, these are also some formulas which are very fundamental. They solve the normalization problem, but also they remember, if you know the Maxwell equations, they are about the electric and magnetic fields, which are kind of dual to each other, in the sense that electric fields can generate magnetic fields, magnetic fields can generate electric fields. And here you have the formulas dealing with the until and the weak until operators, which can also, and it is also, these formulas are regulating the relationship between them. So that's the formal analogy. So, and then when you look at this rewrite system and you then analyze which is the blow up involved in bringing and applying. So you are going to get a delta 2 formula essentially by exhaustively applying these rules. And how much larger can this formula be? You are going to find a single exponential blowup. And what that means is that delta 2 normalization is just as bad as bringing a formula in conjunctive normal form. That can also involve an exponential blowup. So essentially, in my view, this completely demystifies the normalization problem. It tells you normalization in LTL is not expensive. It has just a exponential blowup, but so has the conjunctive normal form. And the algorithm is not at all complicated, and it is purely syntactical. There is no need to go outside temporal logic and move to automata or regular expressions or whatever. Okay, here is an example, but in the interest of time, let me just skip that. And so McFly and Doc have gone back to the past. They have proof now, they have found now this new normalization procedure, and then they go back to today. And if you remember the movie, the idea is that when they come back to the present, then the present has changed because of what they did in the past. And now, again, also, the present is going to have changed because of this new normalization theorem. So what has changed now when they come back? So remember that in the old present, right, what we had was this algorithm due to Kourkoubetis-Ayanakakis, allowing us to go from an arbitrary non-deterministic Büchi automaton to something called a limit deterministic Büchi automaton. And now the idea is that there is a new algorithm for that, for translating a non-deterministic Büchi automaton into a limit deterministic Büchi automaton, which goes through a normalization step. So before starting to construct the automata, you take the formula and first you normalize it, and then you use a new algorithm to go, a specific algorithm for formulas in normal form, to go from the delta 2 formula to the limit deterministic Büchi automaton. And now this is the point at which I have to explain you intuitively what is a limit deterministic Büchi automaton. So a limit deterministic Büchi automaton is an automaton which has two components, an initial component and an accepting component. And both of them are completely deterministic. And on top of that, the only non-determinism in the automaton is caused by the fact that the automaton can jump from the initial component, I shouldn't use blue for that, from the initial component to the accepting component. And now, if you are familiar with Büchi automata, you know that an accepting run must visit the final states infinitely often. And that means that if you want to have an accepting run, then at some moment you will have to jump into the other component. But that's the only point at which you are using non-determinism. The only non-determinism available to you is when to jump. So once you decide I jump, now here everything else is completely determined, right? And now let me just sketch how, or let's say justify for you why the normalization step helps when translating a formula into a limit deterministic automaton. So take a formula like this, and this is not a formula in normal form, because here you have a G inside an F, and then an F inside that G. And remember that F corresponds to until, and G corresponds to weak until. So we have here two alternations. When you normalize the formula, you get something like this. Okay, now this is a formula in delta 2. And actually the only difficulty, let me focus on this part. And let's look at how to translate this part into a limit deterministic automaton. And when we look at this here, there is one alternation. So essentially, we have this until within which we find this G. But there is one alternation, and then that one alternation is going to correspond to the jump. The idea is that here, if you look at this formula, this is telling you that this must hold until this holds. So there is a point at which you decide to forget about this formula and worry only about this one. And that's the point at which this corresponds to the jump. So actually, when you construct the automaton, what you have is an initial component which essentially takes care of this formula, or making sure that this formula is going to hold. But then at some point, you have to take care of the other formula. So you jump, you guess the point at which GB starts to hold, and then you, here in the accepting component, care about the rest of what you have to care about this part, for this part, and then also about the new formula. So you have a very strong relation between the shape of the formula and the shape of the automaton. So, and then let me show you some size reduction. So remember that these were numbers that we were obtaining with the Safra construction. And here there are numbers, you know, actually the construction of Kourkoubetis and Yannakakis, as far as I know, was never implemented. Also because of this combinatorial problems, also because of some problems related to it not being useful for quantitative verification, probabilistic verification. I don't want to get into that. But then compare it with the new approach and the new LDBAs, okay? And as you can see, for example, here, the advantages are enormous. I mean, the speed ups are enormous. Okay, and then the present, so that has changed, but there is also another change. So if you go back to, if you remember the old version of how things were, we had there Safra's procedure for determining omega automata, which was double exponential and very combinatorial and so on. And now again, what we can do is introduce a normalization step. And then again, introduce a dedicated algorithm for going from a formula of this form to what is called a very weak delta 2 alternating Bush automaton, for which then you have a dedicated algorithm to go to a deterministic raving automaton. And again, I don't have time to get into the details, but I think I can give you an idea of why this is a natural match, why it is, these steps are much more natural than what they were before. So it is well known how to go, and this is going to be now part of the talk, a few minutes, where I have to assume that you know what alternating Bush automata are. If you don't know what they are, then just take a nap, and then I will wake you up when we are done, right? But basically, so an alternating Bush automaton is an alternating automaton in which, so you have, you know, steps at which you branch and the automaton becomes true automata, and with a Bush acceptance condition. So if you take this formula, which is not in normal form, again, you can see a G inside an F, and here an F inside a G, and here a G inside an F. So this is going to have even 3 alternations, right? And you then now construct the corresponding weak alternating Bush automaton using a construction that has been known for a very long time. Then you are going to construct the automaton that you see on the slide. And the important thing is that these pink states, they are the accepting states. And then you can see is that the structure of the automaton reflects the alternations. So the alternations between F's and G's, or between untils and weak untils, correspond to alternations between non-accepting and accepting states. Okay, so in this case, you are also going to have 3 alternations between non-accepting and accepting. If you now do the same, but starting with the delta 2 formula after the normalization, then the automaton reflects the new structure of the formula, and you have one alternation. If you start with a non-accepting state, then the automaton, there is going to be at some point a jump to accepting states, but then from now on, all states are accepting, okay? And now, for those of you a bit familiar with translating LTL into automata, then this should immediately ring a bell, because what you are doing is transforming a sort of liveness condition. Visiting infinitely often states here is kind of a liveness condition, okay, into a safety condition, which is, or a co-safety if you want, which means reach final states, because you know that once you have reached final states, you don't have to worry about reaching non-final states anymore. You are already done. And this is what makes the translation from this specific automata with only one alternation to general automata so much simpler, okay? In fact, what you can see is that instead of the states of the final automaton being trees of sets with the huge combinatorial explosion that involves, you only need pairs of sets. And the combinatorial explosion there for pairs of sets is much more manageable than for trees of sets, okay? So that's actually what this new translation brings you. So now for those of you who were sleeping, you can wake up, and now I can just do a little bit of publicity for the tools that have come out of these new ideas. And now you may say, but how can you have produced already tools? I was looking at the bottom of your slides, and I saw, for example, that your last results, the result about normalization, the last procedure for normalization was only a few months old. So how can you have tools which are well developed? You know, this talk is full of temporal twists, and this is the most interesting one. We started doing this research around actually about 10 years ago. So the first paper, our first paper was in 2012. And I must say that this whole line of research was initiated by Jan Kretinsky, who was my PhD student at the time, but who decided to go for it, even though I was a little bit skeptical about us doing this. And then he was joined by Salomon Sickert, and all this tool development has been done by them. So, but the nice thing is that, you know, from the very beginning, this was born as a way of improving the translations, and as an engineering problem. How do we construct automata with fewer states? And from the very beginning, we were starting to have actually success and improving the state of the art. So we were implementing things and improving the state of the art. But the problem is that actually we didn't, or at least that's the way I look at it now, we didn't know which was the theoretical foundation of what we were doing. We were just finding kind of more and more tricks. And if there is any contribution of mine to this work, is that I was very pissed off by this. I wanted to have not only better and better tools, but also some kind of underlying idea of why is it that we are doing this. And finally, you know, in a kind of reversal of time, we have been able, at least in my view, to find it. What we were doing all the time is exploit this normalization algorithm, only in a very weird way. But what happens is that now that the normalization is in place, right, we already know that it works, because actually we have already all the implementation work done by us in the past, right? So actually, if you go now, for example, to OWL, to this tool developed mostly by Salomon Sickert, but also by Jan Kretinsky, there you will find an online demo. And in particular, for example, you can, if you go there, you will be able to, this is not the one I was looking for. So if you go there, then you can here click and, for example, normalize formulas. And you can do much more than that. You can transform the formulas into automata. And so you can do that then immediately after this talk ends. And this is the tool for dealing with LTL and normalization if you want. But there is another tool which is, let's say, the biggest success of Salomon and Sickert, the tool Strix, which is a tool for synthesis, which is applying these techniques that I have been presenting to you in the talk. And this tool, it is, this is the piece of the main argument for my convincing you, if I want to convince you that all this does something. This tool has won the synth competition in the last 4 years in the LTL track of the synthesis competition. Of course, the fact that we have a very efficient transformation of formulas into automata is only one of the components of the Strix, but it is an important component of Strix. It's one of the things that has made it win the competition. And notice that the first time the Strix won was in 2018. We didn't know about normalization then, but actually what we were doing was to exploiting normalization. Okay, so basically that's it from me. And I would just like to conclude by telling, imagine that SAT, that you don't know about the conjunctive normal form. Imagine that you have to rewrite the book on SAT without knowing the conjunctive normal form. It is impossible, right? The conjunctive normal form appears everywhere. Imagine that you have to do the same for first order logic, but without the scholemization, without the Skolem normal form. You are going to be, you have the scholemization. Scholemization is used almost everywhere, even without anybody telling you. And my argument, what I would like you to keep from this talk, is that somehow this is what happened to LTL. The normalization was there, but there was no efficient normalization algorithm, so nobody was paying attention to normalization because everybody thought this is useless in practice. We cannot use it. And now suddenly we can use it. And then any time that you have a new problem concerning LTL, you can think, oh, maybe it's a good idea to normalize first. So that's my message, my last message. And I would like just to thank you for your attention. Thank you very much.
Thank you very much, Javier. What a wonderful success story with beautiful theory and real tools that work. So I would like to invite everybody to ask questions. If you're participating online, yes, then please go ahead and queue up questions. There's already one from Rupak. Yeah, why don't we get started with this one, and then we'll go to the room. So yes, here's Rupak's question. Are there explicit and natural families of LTL formulas for which the new algorithm is doubly exponential?
Yes, so the new algorithm, so you mean, what do you mean by the new algorithm? No, the normalization algorithm is single exponential. So I don't know if, so exactly then what you mean. The normalization algorithm is single exponential.
I'm guessing he means the construction of the deterministic.
Automaton is double exponential. The construction, okay, LTL to LDBA. I think so. Yes, I think so. That I don't know if we have any specific example in the papers, but it is, yeah, I'm sure there is definitely so. Because, the double exponential actually comes from the Boolean operators. So actually, you don't need to go very deep into the temporal operators. It's just the combinations of ors and ands what is going to give you the double exponential. But yeah, I guess that's so. It's a good question. I should have some family to show you.
All right. Maybe let me ask you one question, and then we'll ask the room. You called LTL a syntax for automata, right? But arguably, it's a really bad syntax because LTL cannot express the omega regular languages. So do these results generalize to logics like quantified LTL and other omega complete extensions?
I don't know, but probably not. I mean, you could, for example, think whether you take just any extension of LTL, which is able to express all omega regular languages, and then you could start thinking whether they, for example, the linear time mu calculus, right? And you could start thinking whether they generalize to them. And the answer is basically no. So my counter argument to that is, you could say that if LTL was not so were superseded by omega regular expressions and by the fact that they are more powerful, then LTL would have already disappeared. And still, it is the language that you resort to in most tools. So there is an LTL track in the synthesis competition, but interestingly, there is no extended LTL track, right? So it seems that LTL is enough for many applications. So the argument of the people using automata-theoretic techniques, another one of the algorithms to say, another of the reasons to say is don't pay attention to LTL, do everything with automata, was automata are more powerful. But people continue to use LTL, right? And then if you want, okay, so what I am doing with this talk is also tell you, LTL being a logic matters because this normalization, do it with automata. Get these results with automata, not with logic. And I think it is surely possible because in principle it is, right? But I don't think it is going to be easy. So in particular, these results we could obtain because LTL is a logic and you can use equivalences and you can use a lot of stuff. So you use it again. So you bring back the old motivations of Manna and Pnueli in a sense.
Wonderful, yes. All right, are there questions in the room?
I'm checking. I have one quick question. Javier, you said that the old translation is monolithic. Can you just expand on how the new one is not? I mean, you're referring primarily to the normalization step or also to the subsequent translation to automata?
No, I am talking about the subsequent translation to automata. So the new translation, the old translation is as I said, monolithic. You just given here, this is the automaton. And now the new translation is not, and for the very simple reason that you are attaching one formula or two formulas to every state. So the meaning of a state is actually derived immediately from the meaning of these formulas, okay? And this, first of all, this allows you to use a lot of simplifications, because if you are having two different states, but the formulas that are labeling the states are equivalent, then you are going to be able to merge the states, right? So this is one point. And then another point is that you indeed, the structure of the automaton is going to reflect the structure of the formula. So for example, the limit deterministic automaton is going to have one component for every P1 subformula of the delta 2 subformula or something like that, okay? So actually it is, you cannot say that it's fully compositional, but you see it reflects the structure of the formula much closer way.
Yeah, thank you. Any more questions in the room? So I have one other quick question.
Sure.
So you mentioned also that the limit deterministic automata were initially introduced for probabilistic systems. So if you have...
Yes, they were introduced by Kourkoubetis and Yannakakis in order to do probabilistic verification, yeah.
So have you looked at all at extensions of LTL to quantitative systems like probabilistic systems, but you have similar normalization results?
So I'm not sure what you mean. I mean, so the idea is that you are looking at LTL, and the problem that Yannakakis and Kourkoubetis wanted to solve is, okay, given a probabilistic system, and in particular a Markov chain or an NDP, right? Does it satisfy this LTL formula with probability 1? right? And the problem, and in fact, they gave this solution by using limit deterministic automata. But the problem that they had was that their construction could not be extended to the problem of, does the system satisfy this formula with probability at least this bound? Okay. This is something that our construction does, and the new constructions do. There is not, our construction is not the only one around now, right? So in that sense, this does. So if now you are saying whether, I'm not sure then what kind of extensions are you thinking about? So
yeah,
for example, if you are thinking, sorry, maybe.
Yeah, I was thinking maybe timed LTL or similar.
Timed LTL. There I have no idea. It might be the case that it is there could be some extension. I don't know.
Yeah, thank you.
I have maybe one last question, but I don't want to keep the room from asking questions. You mentioned that the original motivation for the normalization was the idea of having deductive proofs and so forth. And somehow this has laid dormant for quite a while now. Do you think that this could, revive deductive approaches? I mean, after all, I guess this would dramatically simplify the deductive proofs if you have a smaller normal form.
Well, that's true, and yes, I think it might. And in particular, if some of this can be extended, for example, to fragments of first order LTL, where it would be even more useful. And I think I don't expect it to be extensible to, but to useful fragments, I think that could certainly be the case. And yes, I mean, this is what I was saying at the end, right? There is almost, when you are doing SAT, there is almost no case in which putting the formula in conjunctive normal form or disjunctive normal form or something doesn't help. It's something that you do almost routinely, right? And that's something that you should now do whenever you are doing LTL. Think, would I profit from putting this in normal form? Because it's cheap, I can do it, right? So yes, I think this could definitely help for deductive proofs, yeah.
All right, final chance for a question from the room.
I don't see any right now.
I guess no, we're already 8 minutes into the break, so that's
okay. So thank you very much for your attention. So
thank you very much, and yeah, we'll reconvene in 12 minutes, I guess.
Right. Greetings to Philadelphia. Sorry I couldn't be there, and